All right, in this chapter we're going to do some more graph theory. We're going to look at algebraic properties of graphs, which essentially, when you talk about algebraic properties, we are discussing like structure of graphs. And so we're going to start by defining a special kind of function from one graph to another. So we have a function, if we have a function f from the graph G to the graph G prime, that function is a homomorphism if it satisfies the following properties. The first one says if E is an edge in G, then f of E is an edge in the graph G prime. So this just says it has to map edges to edges. And part B says that it has to map vertices to vertices. Now, the first two properties here, this is just what it takes for f to be a function. Any function between graphs will satisfy those two properties. The homomorphism property is in part C here. So the homomorphism property just preserves kind of connections. So if U and V are vertices in G and they're connected by some edge, which we're going to call E. So here's my vertices, there's my edge E. Then in the graph G prime that it's mapped to, if U and V are mapped to these two vertices, then that means that this edge has to be mapped to this edge. Okay, so it preserves that connectedness. So we're going to look at a couple of theorems. We're not going to prove the results in Theorem 5.1. We'll kind of discuss them and see why that seems like they should be true. We're going to prove some results in this section, but there's some theorems that we'll just sort of state without proof, and you might try them as an exercise. So suppose we've got a homomorphism from G to G prime. Then f of G is the subgraph of G prime. It is, first of all, a subgraph because it's mapped into G prime, so it's got to be contained in that. And it maps vertices to vertices and edges to edges. So it is the subgraph of G prime that contains those vertices and those edges. It's a subgraph, so note that not every vertex and edge in G prime has to be hit by a vertex or edge in the original function, right? We can map a smaller graph into a bigger graph. If G is connected, then f of G is connected, and that's really because of this homomorphic property that preserves that connectedness. So if edges were connected in G, they have to be connected by the edge f of E in G prime. And a result, kind of an immediate result of part B is what we have in part C. If G is complete, then f of G is complete. Remember that a complete graph is the graph that has all possible edges drawn. So, for example, I might map the graph K4 into the graph for K5. And the only way I can do that is if the subgraph that I'm mapping to is also a complete graph. In fact, it'll look just like K4. Maybe I send this this vertex to this vertex, and I could send this vertex to this vertex. Now, it doesn't even have to be, I just said that what K4 maps into will look just like K4. That's not necessarily true because I could map two vertices in K4 to the same vertex in K5. Like perhaps I take these two vertices and they're going to both map to this one. Right? So this would not be a one-to-one function of vertices, but it would still be a mapping. So I've got this going here, and that also mapping there. So then if we kind of line up the edges, so these two, that edge rather, the edge connecting those two vertices has to map to the edge connecting the vertices that they map to. And this vertex here, I'm going to highlight it in blue here. I've got an edge mapping this vertex down to that vertex, has to map to this edge here. And that also takes care of this edge, right? Because the edge that connects those two has to connect the vertices that these map to over here. This edge just goes away because these two vertices map to the same vertex there. So there's an edge. We're not going to draw an edge from a vertex to itself. This edge, these two edges here are going to both end up being mapped to this edge here. And so the image of the K4 graph under this mapping ends up looking like K3, right? I kind of collapse two vertices into one, but it's still a complete graph. If I had mapped these two vertices to two distinct vertices over in K5, then the image, the graph that it maps, its image in K5 would look just like K4. So next, if I have a homomorphism but I impose another criteria, which is that these mappings from the vertices to vertices and edges to edges are both one-to-one, and I left this out of the definition, and are surjective, so they're also onto, then we say that function is an isomorphism. So isomorphism, like the root of that word just means same shape. And if we have a function that is an isomorphism from G to G prime, then G and G prime are isomorphic. And an intuitive sense of what it means to be isomorphic, for two graphs to be isomorphic, is just a relabeling of the vertices and edges. They have the same structure exactly. Now we're going to look at another type of function. First, a definition that'll help us build this new type of function. So let's say we have a graph, and we have an edge connecting a couple vertices in that graph. So we're calling that edge E, and we're supposing that it connects the vertices V1 and V2. Now let's say I make a new vertex. I add a new vertex, and I basically split one edge into two edges. And the way I do that is I take this edge E, and I replace it with two edges. The edge that goes from V1 to V, and then V to V2. If I do that, then this new graph I created is called an extension of the graph G. And if I do that like maybe a bunch of times, then we say that the one graph is derived from G1. So an extension of a graph is basically just by taking a vertex and adding it to an edge that already exists and doing that however many times I want, right? So I'm splitting one edge into two edges. And two graphs are homeomorphic, not homomorphic, but homeomorphic if they're both derived from the same graph. So we're going to get used to these, or get a feel for these definitions in these next examples. In 5.1, we want to draw an extension of the graph. So that means I'm just going to do this process once. I'm going to pick an edge. I'm going to split it into two edges by dropping a vertex on it. So maybe I do that to this edge here. Maybe I'll call this vertex F. And so now I've replaced the edge AD. There is no longer an edge from A to D. There are a pair of edges from A to F and from F to D. So that is an extension of the graph. In 5.2, we want to determine if these two graphs are homeomorphic, and we just want to see if they were derived from the same graph. Now, just looking at these graphs, I've got a feeling that maybe they are derived from the same graph. They seem to have the same kind of shape, right? Although they don't have the same number of vertices and they don't have the same number of edges, so they certainly can't be isomorphic. But they seem to roughly have the same shape. So it looks like, for example, that on the left, this graph was maybe derived from another graph by adding a vertex here and here and here. And this graph on the right looked like it could be derived from another graph by adding those two vertices. And now to kind of reverse that process, I'm going to take on the left, say, if I focus on that edge that goes from H to E in the middle of the graph here, the edge that goes, or the pair of edges from H to G and G to E, I'm going to kind of collapse that into one edge. I'm going to get rid of the vertex G, and I'm going to do the same thing to get rid of vertices B and D. So now I've got vertex A, C, F, H, and E. And it looks like this is also kind of the source graph. Maybe I shouldn't use that term. Like the original graph from which we could have derived the graph on the right as well. So it looks like both graphs are homeomorphic to this one. Both graphs are derived from this one, which means that they are homeomorphic to each other. So this statement gets a big yes. We have determined that they are homeomorphic. So when we make an extension of a graph, right, when we go through this process that just says I'm going to take an edge, split it into two edges by putting down a vertex. Look at these vertices, right, that are highlighted in yellow in these two graphs. Whenever I do that, I'm basically just adding a vertex that has degree 2, right? That's the only possible option when I go through this process. So if I have one graph that is an extension of the other graph, I cannot possibly have added any vertices of odd degree. So G and G prime must have the same number of vertices of odd degree. And that leads us to the following results. If G and G prime are homeomorphic, then they both have the same number of vertices of odd degree. So if they were both derived from the same graph, they have to have the same number of vertices from odd degree. That's really just a direct result of that observation that we made. And if we think back to what we looked at in the last chapter, if they have the same number of vertices of odd degree, then if G and G prime are homeomorphic, then either they both have an Euler cycle or they both don't have an Euler cycle. And same if they both have a proper Euler path, or neither of them have a proper Euler path. Remember, we had a nice result that just said that that a graph has an Euler cycle if every vertex has even degree, and a graph has a proper Euler path if there are precisely two vertices of odd degree. All right, so some more definitions. Let's say we've got a graph G and we have a bunch of subgraphs, right? So like G1, G2, those are all subgraphs. Then I can make another subgraph G prime by just taking the union of those subgraphs. So you just throw all the edges together, throw all the vertices together, right? So a vertex is in the union if and only if it's a vertex in one of these G sub i's. An edge is in the union if and only if it's an edge in one of those G sub i's. And then we define the intersection similarly. So, you intersect the vertices and intersect the edges to get the intersection of the graph. We say that a collection of subgraphs are pairwise disjoint if no two of these G sub i's have any vertices or edges in common. Okay, so a couple more results and then some more definitions. Whenever we start a new chapter, it seems like we've got a lot of definitions to get through. Theorem 5.4 says if we have a couple of distinct components of a graph, then those two components are pairwise disjoint. So remember that a component is a maximal connected subgraph. And every graph then can be seen as the union of its pairwise disjoint components. And really, I guess in Theorem 5.5, this is maybe a little bit redundant or in the way it's stated. We said that this theorem says every graph is the union of its pairwise disjoint components. Well, components have to be pairwise disjoint, so we just know that every graph is the union of its components, and they happen to be pairwise disjoint. We've been focusing a lot on subgraphs. In this next definition, we're going to define the complement of a graph, which is very specifically not a subgraph of G. So if I have a graph that has some vertices and edges, then its complement is I have to take all the same vertices. But the edges is basically just taking the complement of the edges. We would draw, an edge is drawn in the complement if and only if the edge is not there in the original graph. So, for example, let's say G is the graph with these four vertices. And I've got maybe these edges. Then the complement, which we write as G superscript C, I have to have the same vertices. And I'm just going to draw precisely the edges that are not included in the original graph. So I'm going to draw an edge from A to B, from B to D, and from B to C. And then I think that's it, right? So that's all the edges that were not drawn in the original graph. Back to subgraphs, if we have a subgraph of a graph G, we call it a spanning graph. It includes all the vertices. It doesn't have to include all the edges, but it has to include all the vertices. And if a spanning graph is a tree, we call it a spanning tree. So we're going to do some examples here. Here's a graph. We're going to first draw the complement. So let's say this is the graph G. Then the complement, I'm just going to start out, it's got to have all the same vertices. So it's got these 6 vertices. You might notice that the graph that they gave us is the complete bipartite graph. So it's not a complete graph itself, but it's, we've got these 2 sets of vertices, and all the edges that can be drawn between the 2 sets are included, and none of the edges within the 2 sets. So then it's maybe not too surprising that the complement will have no edges in between the 2 sets, between the top and the bottom. Because I cannot include an edge if it was included in the original graph. I have to include an edge if it wasn't included in the original graph. So from A to B, and B to C, and then from A to C. And then likewise on the bottom, this will look kind of the same. This is the complement. A spanning graph just has to include all the vertices. It says nothing about the edges that it has to include. I guess I could include no edges if I wanted to. But maybe I'll include these. I'll say A is connected to these. I can only, since it's a subgraph, I can only include an edge if it was already part of the original graph. But I can choose which edges I want to. So this is a spanning graph. Notice that a spanning graph doesn't have to be connected, right? I mean, it's a subgraph, it just has to include all the vertices. A spanning tree, however, would have to be connected because a tree is connected. So a spanning subgraph has to include all the vertices, and if it has to be a tree, then there has to be a path between any two vertices. So drawing a spanning tree, again, since it is a subgraph, I can only include edges that were already included in the original. But I just want to make sure that it's connected, that every graph gets hit, and there's a path between any two vertices. So there we go. There's a spanning tree. It is connected. The other thing that makes it a tree that's important is that there are no cycles. So this is a spanning tree, which means it's connected and has no cycles. It's not the only spanning tree. You might come up with some other ones. All right, so now we're going to explore connectedness a little bit more. If I've got a graph, then a set of edges, so a collection of edges from, not all edges, but just some collection of the edges that are in G, we call it a cut set if removing those edges means that the graph is no longer connected, but removing any proper subset of C leaves the graph connected. So it's it has to, removing those edges has to disconnect the graph. And you have to remove all the edges in C in order to disconnect it. So if the set C consists of just a single edge, then we call that a cut edge. In this graph, we could find a couple of cut edges. For example, this E5 is a cut edge because if I remove that edge, then I can't get from V5 to any other vertex. Similarly, E6 is a cut edge because if I were to remove that edge, then I couldn't get from get from any vertex, say in this bottom part to this top part. It would disconnect the graph. So these are cut edges. In the next graph, we're going to find a cut set. So notice this graph doesn't have any cut edges. If I remove a single edge, regardless of which edge I pick, the graph will still be connected. And let's see, I'm going to start out just by labeling these edges. So E0, E1, E2, and so on. If I were to remove the edges E0 and E2, then that would lead to this graph here. So that's a cut set, right? Because then I can't get from this vertex up here in the upper left to any other vertex. If I remove the edges E2 and E5, for example, that would give us removing E2 and E5 gives us this graph. So that's a cut set. It's a cut set because removing those edges causes the graph to no longer be connected, and if I removed a proper subset, like in this one, if I only removed E5 and didn't remove E2, then I would have this edge and it would be connected. So it is actually a cut set. A couple more results now. Suppose we have a spanning tree of a graph. So a spanning tree has to have all the same vertices, and then it's some collection of edges, and it has to be connected with no cycles. So if I have a spanning tree, if T is a spanning tree and C is a cut set for the graph, then their intersection is non-empty, meaning if you have a spanning tree, then if you look at the edges of a spanning tree, then it will contain, no matter what cut set you find in the graph, it'll overlap somewhere with that cut set, with that tree. And in Theorem 5.7, we say that an edge E of a graph is a cut edge if and only if it's not an edge in a cycle. We're not going to prove this, but I think it kind of is a little bit intuitive. So a cut edge, remember, means that if I remove just the single edge, the graph is not connected. So if that edge were a part of a cycle, right? So like, let's say I have an edge, maybe I'm talking about this edge right here, right? I'll call that edge E. And then, maybe I've got some other stuff, I've got some other vertices, going on down here. If this edge is a part of a cycle, then if I remove it, that means I must have another way to get from A to B, right? If it's in a cycle, just go the other way around. So any path that went, from one vertex to another, any path that traversed that edge E that I want to remove, I could just replace that edge with this path where I go the other way around the cycle. We are going to prove a result in just a moment. First, one more definition. I'm sure we're getting tired of new terms, but we know what a cut edge is. A cut vertex, which is also called an articulation point, is a vertex for which if I were to remove that vertex and the edges incident to that vertex, then the graph is no longer connected. Remember, I can't just remove a vertex without also removing the edge. You can't have an edge to nowhere. So if you remove a vertex, you have to remove the edges that connect to it. If a graph has no articulation points, it's we say that it is bi-connected. That's like a really stronger type of connectedness. So now we're going to prove a result here. In Theorem 5.8, we're going to show that a vertex A of a graph is an articulation point if and only if there exist distinct vertices V and W such that every path from V to W goes through A. Like, if a graph is an articulation point, that means that like removing that vertex and the edges incident causes it to no longer be connected. So in a sense, we're saying that graph really depends on that vertex to retain its connectedness. And in Theorem 5.8, we're going to show that if we have an articulation point, it must be the case that every path between any two vertices has to go through A. And this is also an if and only if. So if I know that for every distinct pair of vertices, every path goes through A, then A must be an articulation point. So it's an if and only if, but it doesn't take terribly long to prove. We're going to go in this direction first. So we're going to suppose that there are two vertices, V and W, such that every path from V to W goes through A. So then what happens if we remove A? If every path from V to W goes through A, then if we remove A, there must be no path from V to W. and that means that G is no longer connected. And that's precisely what it means to say that A is an articulation point. To go the other direction, we're going to prove the contrapositive. And to prove the contrapositive, we're going to suppose that for every pair of distinct vertices, there is a path between them that does not go through A. With the contrapositive, remember, we're going to suppose the negation of the then statement. So we're going to suppose that there do not exist vertices such that every path between them goes through A. So what that means is that every pair of distinct vertices, there's a path that doesn't go through A. Okay, so every pair, I've got a way to get from one vertex to any other vertex that does not depend on the existence of that vertex A. So if we remove A, that means there's still a path between any two vertices, and G is still connected. And if removing A doesn't disconnect G, that means that A is not an articulation point. Okay, so let's look at an example. We're going to find some cut vertices in this graph. So we want to find a vertex such that when we remove it and we remove all the edges that are connected to that vertex, then the graph is no longer connected. So I think there's probably several we could pick, but for example, V4, that's a cut vertex or an articulation point. Because if I were to remove that vertex, and which causes me to also remove the edges connected to that vertex, then I can't get from V5 to anywhere. Similarly, like V6 is an articulation point. If I were to remove V6 and the edges that are connected to it, say that one, that one, that one, then I can't get, that sort of disconnects this part of the graph from the remaining part of the graph. So those are two articulation points. There are more. You could identify some more. Okay. Oh, bad line break here. So first a theorem where we're going to define a relation. So we've got a connected graph, and we're going to define a relation on the edges, and we're going to say that two edges are related if they're either the same edge, so every edge is related to itself, or there's a simple cycle in G that contain E1 and E2 as edges. This is an equivalence relation on the set of edges of a graph. And if you have an equivalence relation, then one thing you can do is determine its equivalence classes. So each equivalence class, which we're going to call E sub I for this equivalence relation, we can take a look at those edges of the equivalence class and then grab the vertices that are connected, right, that are incident to those edges. And that is a subgraph of G, and we call it a bicomponent of G. So I'm going to just draw a quick example here. So let's say I'm just going to start out by drawing G. Notice, so this is G. G has one component, right? I mean, the G itself is connected, so it consists of one component. The bicomponents, though, are going to be the subgraphs defined by these equivalence classes. So edges are related if they're contained in a common simple cycle. And so these edges that I'm highlighting in yellow, these are all related. Right? No matter which two edges I pick that are highlighted in yellow there, I can find a common simple cycle that connects them. For example, you might say, well, what about this one here and this one here? And then I would say, oh, it's just this simple cycle right here. So remember, a simple cycle doesn't repeat any vertices. And so no matter which two edges I pick that are highlighted in yellow, I can find a simple cycle that contains both of those edges. So this is a bicomponent. Similarly, this one over here in blue, that's a bicomponent, right? Because that is just a single simple cycle. And then the other part, remember this definition says, oops, they're related if there's a simple cycle containing both of them, or if E1 is equal to E2, if it's the same edge. So this edge is related to itself. So this graph has one component, but it has three bicomponents. All right, we're going to establish another result here. Suppose we have distinct edges of some bicomponent. Then we know there's a simple cycle in that bicomponent containing A, B, and C, D as edges. Now when you read this, you might think, isn't that just the definition of what it means to be in a bicomponent? But the definition says that they're in the same bicomponent if there's a simple cycle in G, in the overall graph that contains them both. This, we're going to be more specific. We know that there's going to be a simple cycle in that bicomponent that contains them both as edges. So let's let AB and CD be distinct edges of a bicomponent. Right, the bicomponent that is that subgraph, and we know that if they're distinct edges in that bicomponent, that they're both edges in the set E sub I. Now, if they're both edges in E sub I, that's an equivalence class. That means that they have to be edges of a common simple cycle in G. So there is a simple cycle in G. Containing these as edges. Now, let's suppose, for contradiction, that there's an edge in the cycle that is not in E sub I, right? We know there's a simple cycle in G that contains those as edges. We want to show that that simple cycle is actually contained in this bicomponent. So we're going to go for contradiction here. So let's suppose that there's an edge, say EF, that is not in that bicomponent. So if that's true, right, if EF is not in this bicomponent in E sub I, is not in that equivalence class, that means that we have edges from two distinct equivalence classes in the same simple cycle. So that means that our equivalence classes overlap at the edge EF. Now, hopefully, this raises your hackles a little bit. If our equivalence classes overlap, that should kind of give us some pause, because we know that in any equivalence relation, the equivalence classes have to partition the set. So our equivalence classes cannot overlap at a single edge. So let me just get that down. So our equivalence classes partition the set. And that means that this edge, EF, must be in the same set, E sub I. Right, so the fact that equivalence classes partition the set, this was our contradiction. Right, we suppose that EF was not in E sub I. That led us to this contradiction. And that means that EF has to be in the same set, E sub I. And that means that this simple cycle that we know exists in G, that includes the edges A, B, and C, D, in fact, have to be in the same bicomponent. Okay, so we've got a few more results here. We're going to prove two of them. So Theorem 511 will state this without proof. But if a bicomponent consists of a single edge, then E sub I is a cut edge. I'm going to go back to an example we drew when we were looking at what bicomponents were. So there were three bicomponents, the one highlighted in yellow, the one highlighted in blue, and then the one highlighted in green. So that bicomponent, the green one, right, that consists of a single edge, and that edge is a cut edge, right? If I removed it, then the graph is no longer connected. This theorem simply says that that'll always be the case. If a bicomponent is just a single edge, then that edge has to be a cut edge. Theorem 5.2, which we'll prove, says if for every two distinct edges, if every two distinct edges are edges of a common simple cycle in the graph, then that graph has to be biconnected. Meaning, remember, biconnected means that there are no articulation points or no cut vertices. So we're going to prove this one. We're going to suppose that every two distinct edges are edges of a common simple cycle in G. We want to show that G has no articulation points. So we're going to let U and V be any two vertices in G. I just want to grab two arbitrary vertices. I know that this graph is connected, right? Every two distinct edges are edges of a common simple cycle. So I can get from vertex from one vertex to another. So let's let U and V be any two vertices in G. And let's let A be a vertex on the path from U to V. So what we're going to do here is show that this vertex A is not an articulation point. So because I selected U and V as to be just any two, arbitrarily chosen vertices, and A is just some vertex on the path, if A is not an articulation point, that means that the graph G can't have any articulation points. We're going to show that A is not an articulation point, which means we're going to show that the path from U to V doesn't depend on A. So let's consider this path. So I'm just going to kind of sketch it out. So let's say I've got this vertex U, and I've got some other vertices, and it's eventually I'm going to get to vertex V here. I've got some other vertices, and I've got this path along the way. And I'm going to start by saying, suppose I've got this vertex A in the middle, and I'm just going to consider the edges, right, that connect to A. So maybe here's vertex C, and here's vertex B, right, and then the rest of this goes. Right, so here's sort of pieces of the path from U to V. So we're going to let CA and AB be edges, distinct edges on the path from U to V. So I've got these two distinct edges on this path. I know that by supposition, every two distinct edges in the graph are edges of a common simple cycle. So I know that that's true about CA and AB. And I'm just going to kind of sketch that out. So I know that there's some simple cycle, right, that contains C and B, or that contains those two edges, CA and AB. Oops. All right, so what that means is that we have a path from C to B that doesn't go through A. And if I've got a path from C to B that doesn't go through A, then I have a path from U to V that doesn't go through A, because all I got to do is traverse this path, and then at the point where I was about to pass through A, I'm just going to go the other way around that cycle, and then, continue on my merry way. That means that A is not an articulation point. And if A is not an articulation point, then G has no articulation points, and so G is biconnected. Okay. Our last theorem of this section just says, suppose I have a couple of bicomponents, then the vertices of these two bicomponents, right? So the vertices that make up the first one, these vertices that make up the second one, they overlap at most at one vertex, right? So two bicomponents can share a single vertex. They don't have to. They can share a single vertex, but not more than one. And I'm just going to first show you what I mean by looking back at an example that we looked at before. Again, I'm going to go back to this graph with the three bicomponents. So the yellow and the blue bicomponent don't share any vertices in common. The yellow and the green share this vertex in common. The green and the blue share that vertex in common, but you can only share one, there can only be one common vertex. So either two bicomponents either have no vertices in common, or they might have one in common. And we're going to prove that. We're going to do this by contradiction. So let's, by contradiction, let's suppose that Vi and Vj contain a couple of vertices in common. So suppose their intersection has two vertices. I'll call them A and B. So A and B are in Vi, and they're also in Vj. So if A and B are in Vi, that means that there are edges in E sub I that connect these vertices. So let's see. So let's say I've got some edge that connects a couple of vertices, say A and C. And so, A is connected to some vertex. B is maybe connected to another vertex by a single edge, say vertex D. So these are edges in E sub I. Oh, sorry, that's a little redundant there. So there are edges in E sub I that we've listed here. And if these are two edges in E sub I, then there's a simple cycle in the bi component, G sub I, that contains these two as edges. And you know, I've been using parentheses, but I should be using braces for edges. So I know I've got a simple cycle in this bicomponent that contains these two edges, and that means that we have a path from A to B in G sub I. Okay. So I know there's a path from A to B in G sub I. We can construct an identical argument and show that there's a path from A to B in the other bicomponent. So similarly, I won't write out all the same steps, but you could, if you just pick two other edges, if you know that they're in V sub j, then you've got a couple edges in E sub j, and there's got to be a path from A to B in G sub j. So it's the same exact argument. If A and B are in V sub j, then there is a path from A to B in G sub j. And in fact, I'm going to actually state this in the other direction. There's a path from B to A. In G sub j. So now, the rest of this is pretty constructive. Consider the following path. Got a path from A to B in G sub I. So I traverse that path, I end up at B, and then follow that up with the path I know exists in G sub j from B to A. That's a cycle, right? It starts at A, it ends at A. That is a cycle, and so every cycle contains a simple cycle. So now we know that there's a simple cycle that contains edges from both E sub I and E sub j. that's a contradiction, right? The edge sets of these bicomponents partition the set of edges. These are equivalence classes. So this is our contradiction, and this contradiction implies that the two vertex sets contain at most one vertex.